Start by exploring the fundamental concept of reflection of light. When a ray of light strikes the boundary between two different media and bounces back into the original medium, we call this phenomenon reflection. The angle at which the light hits the surface, known as the angle of incidence, is always equal to the angle at which it reflects, called the angle of reflection. This is a key law in optics. After reflection, the light's velocity, wavelength, and frequency remain unchanged, but its intensity decreases. If the reflection occurs from a denser medium, there's an additional phase change of pi, which is an important detail in wave optics. Real images are formed when reflected rays actually meet, while virtual images appear to meet but don't physically converge. This distinction is crucial for understanding how mirrors work and sets the stage for our deeper dive into plane and curved mirrors. Now let's focus on plane mirrors, which are flat reflective surfaces we encounter daily. The image formed by a plane mirror is always virtual, upright, and laterally inverted, meaning left and right are swapped. The image appears to be the same size as the object and is located as far behind the mirror as the object is in front. When two plane mirrors are inclined at an angle, multiple images can be formed, and the number depends on the angle between them. The mirrors are parallel, an infinite number of images appear. Another interesting property is that if a plane mirror is rotated by a certain angle, the reflected ray turns through twice that angle. Also, if you move towards a mirror, your image moves towards you at the same speed, but the relative speed between you and your image is doubled. These principles are not just theoretical, they have practical applications in daily life and technology. Moving on to curved mirrors, which include concave and convex types, these mirrors are segments of a hollow sphere with one polished surface. The main terms to know are the pole, the center of the mirror's surface, the center of curvature, center of the sphere, radius of curvature, principal axis, focus, and focal length. Concave mirrors converge light rays while convex mirrors diverge them. The position and nature of the image formed depend on the object's location relative to the mirror. For example, a concave mirror can produce real inverted images or virtual upright ones, depending on where the object is placed. Convex mirrors always form virtual diminished and upright images. The sign convention is essential. Distances measured in the direction of the incident ray are positive, and those against it are negative. Understanding these properties helps in solving problems and in real-world applications like vehicle mirrors and telescopes. Wrap up, let's discuss the mirror formula and magnification, which are vital for quantitative analysis in optics. The mirror formula relates the object distance, image distance, and focal length. When f equals 1v plus 1, you always use the correct sign convention when applying this formula. Magnification tells us how much larger or smaller the image is compared to the object, calculated as the ratio of image height to object height. For lateral or transverse magnification, the object is perpendicular to the principal axis, while longitudinal magnification applies when the object lies along the axis. These concepts are not just academic, they're used in designing optical instruments, from shaving mirrors to telescopes and vehicle mirrors. Remember, the focal length of a mirror is independent of the material or medium, and the power to converge or diverge light remains unchanged. Mastering these formulas and conventions is key to solving real-world optics problems.